Hi learners, welcome to my YouTube channel. So in today's class, we're going to discuss dimensional analysis. So what is dimensional analysis? So dimensional analysis is the process used in physics to determine the nature of physical quantities. It is also used to find the relationship between two quantities when mathematics seems difficult. So we use dimensional analysis for various purposes. We use it to find the relationship between two physical quantities. We use it to determine the appropriate unit of any physical quantities. We also use it to derive formulas and units. So to find the dimension of several quantities, we're going to adopt the fundamental quantities in finding the dimension of different quantities. So let's get started. Starting with magness, we have speed. Speed can be defined as the rate at which a body covered a distance. Speed can be defined as the rate at which a body covers a distance. Mathematically, speed can be expressed as distance over time taken. Distance over time taken. Now, distance as a fundamental quantity can be expressed as L and the time as T. So we can re-express this in index form by saying Lt raised to the power of what? -1. This is an expression in index form. And from this place, we can also determine the unit of speed by writing meter per second. Let's move on to the next quantity. So Lt raised to the power of -1 is the dimension of speed. Let's discuss the next one, velocity. Velocity. And velocity can be defined as the distance covered in a specific direction. The distance covered in a specific direction. Mathematically, it is also the speed of an object in a specific direction. So mathematically, we can express velocity as displacement over time taken. Now, displacement is also talking about distance, but distance in a specific direction. So we can still express displacement as letter L, then the time as t. So expressing this in index form, this will be Lt raised to the power of -1. Therefore, the unit of velocity is also meter per seconds. Number 3, acceleration. An acceleration can be defined as the rate of change of velocity with time. And this can be re-expressed as change in velocity with time. And this can be expressed mathematically as v minus u over t. Now, let u be equals to 0, which is the initial velocity. Therefore, acceleration will be v over t. Now, we have already found the dimension of velocity earlier, and the dimension of velocity is Lt raised to the power of -1 over t. Now, we can re-express this as Lt raised to the power of -2 in index form, and the unit will be meter per seconds square. So this is the dimension of acceleration. Let's move to the next one, force. Let's find the dimension of force. And don't forget, we define force as an agent that tends to change the position of an object either on a straight or circular path. And the formula to calculate force is mass times acceleration. Mass times acceleration. Mass still remain m times, we have already found the dimension of acceleration earlier, which is Lt raised to the power of -2. Therefore, force will be expressed as mLt raised to the power of what? -2. And the unit for force can be derived from this place as kilogram meter per second square, but the general unit of force is Newton. Now, number 5, we're going to discuss pressure. And pressure can be defined as a force acting perpendicular to the surface area of an object. Mathematically, pressure is equals to force over area. Force over area. Now, we've already found the dimension of force area, which is mLt raised to the power of -2 over, now, the dimension of area is L raised to the power of 2, because we have length times breadth. Length and breadth are also talking about distance, which is expressed as L in fundamental expression. So we can reduce this. L cancel out L here. We have one L left. So this will be re-expressed as mt raised to the power of minus 2 over L. And we can re-express this as mL raised to the power of minus 1 t raised to the power of minus 2. From this expression, we can have kilogram per meter per second square. But the unit of pressure is given to equals to Newton per meter square. That's the unit of pressure, or it can also be measured in Pascal or Pascal. That is the unit of pressure. Now let's move to the next one, which is momentum. So momentum is the product of change in velocity. The momentum is read as the product of change in velocity. And mathematically, momentum equals to mass times velocity. Momentum equals to mass times velocity. Mass still remains what? Letter m times. We've already found the dimension of velocity earlier, which is Lt raised to the power of minus 1. So momentum can be expressed as mLt raised to the power of what? Minus 1. So the next one we're going to discuss is density. Density. So density is the mass of an object per unit volume. Mathematically, density will be equals to mass over volume. And we can express mass as m. Don't forget the unit of volume is length times breadth times height, and we can re-express as L raised to the power of 3. So expressing this in index form, your m will be equals to L raised to the power of minus 3. This is the dimension of density. So we consider the next one, which is work done. And work can be regarded as the product of force and distance moved in a specific direction. Mathematically, work is equal to force times what? Times distance. And we've already found the dimension of force earlier, which is ml t raised to the power of minus 2 times L. Now, if we multiply this length times length, we're going to be having ml raised to the power of 2 t raised to the power of minus 2. So this is the dimension of work. So the next one we're going to consider is power. Power. So what is power? Power is the rate at which work is done. It is also regarded as the rate at which energy is expanded. So mathematically, power equals to work done over time taken. Work done over time taken. And we've already found the dimension of work earlier, which is ml raised to the power of 2, t raised to the power of minus 2 over t. Now, to re-express this, we're going to be having ml raised to the power of 2 t raised to the power of minus 3, expressing this in index form. So the next one we're going to consider is moment. And what is moment? Moment is regarded as the turning effect of force about a point. The turning effect of force about a point. Moment is also regarded as the product of force applied and the perpendicular distance. Moment is also regarded as what? The product of force applied and the perpendicular distance. That is, moment will be equal to force times distance. Force times distance. We've already found the dimension of force earlier. Therefore, force will be equal to ml t raised to the power of minus 2 times L, which is the distance. So if we equate this now, we're going to be having ml raised to the power of 2 t raised to the power of minus 2. So from this place now, we can also determine the unit of what? Of moment. And the unit of moment is in Newton meter. The unit of moment is Newton meter. So the next one we're going to consider is impulse. So an impulse is the change of momentum of the body. Mathematically, impulse equals to what? Force times distance. So we've already found the dimension of force earlier, which is equals to ml t raised to the power of minus 2 times what? Times L. So we can re-express this as ml t raised to the power ml squared t raised to the power of minus 1 minus 2. So let's consider other quantities. Let's consider the kinetic energy formula. Let's find the dimension of kinetic energy. And the formula for kinetic energy is 1 over 2 mv squared. So having this now, we have 1 over 2. Your mass still remain your mass, but velocity now this time around is equals to L t raised to the power of minus 1 Now everything raised to the power of 2. If we open the bracket now, we're going to be having 1 over 2 ml square t raised to the power of minus 2. So this will be the dimension of kinetic energy. Let's take two more. The next one is stress. And mathematically, stress equals to force over area. Stress equals to force over area. We've already found the dimension of force, and the dimension of force here is ml t raised to the power of minus 2 divided by what? By L square. If we reduce this, our dimension for stress will be equals to m L raised to the power of minus 1 t raised to the power of minus 2. Let's take one more. Strain. Now, strain equals to elongation over length. Now, elongation and length, they are still talking about what? Distance between 2 points, which is L over what? Over L. This will give us 1. So in the next class, we're going to continue with the dimension of other quantities.